So can anyone tell me, and of course your colleagues, what we have covered last Friday? Anyone? Like, I just want to kind of refresh your memory a little bit. Okay, so last Friday we covered the concept of set and also set operations, and also talk about the order pair functions. Of course, we have like 3 types of functions here: one-to-one, onto, and bijections. And we also talk about the cardinality, right? We also proved that the cardinality of rational number equals the cardinality of natural number. We also talk about the sequence and subsequence. And you say soup, right? Like soup and if. We talk about the soup and if of a set, and also cover some technique of proof and the necessary and sufficient conditions. And today we are going to, so I already published the solution for the exercise for topic 1, and you can check it on my personal website. I also upload the lecture recording, but I still try to figure out a way to combine them together, because right now they are kind of separated into several clips and it's hard to watch. Okay, but just give me some time. When I fix it, I will let you know. Okay, and if you have any questions, of course, feel free to email me and come to me during the office hours or TA as well. Okay, so today we are going to cover the metric space and convergence and some topology here. Right, so let me start with the first definitions of today. The order set. So an order set is a set, like a set with order. So that's why I say it. So this is a set X equals with the relation less than. Okay. And this order satisfied the following property. Says that if we have 2 elements from the set X here, then one and only one of the statement will be true among the 3 statements. It could be X is less than Y, or X equals Y, or Y is less than X. So if you think of real numbers, then it's quite intuitive. Also, the second property is transitivities here. Says that there are 3 elements from X here, and you already know that X is less than Y and Y is less than Z. Then naturally you will know X is less than Z here. So these are 2 properties that order set has to satisfy. And within this order set, we can kind of define or find a kind of spatial sequence axon here. It has the following property. When we call that sequence is monotonic increasing, it means that for each elements of that sequence axon, the next elements will be larger, or at least equal. Okay, so you will see that sequence keep increasing, or at least they will stay horizontal here. Of course, we can define monotonic decreasing sequence in an opposite way, which means that the next elements of that sequence is going to be smaller or at least equal. So when you draw a graph, so you will see monotonic increasing function look like let's say that this is the index numbers and this is the, so you look like this one. This is monotonic increasing. And similarly, you can have tonically decreasing sequence. Okay. Right. Then is this upper bound property here. Okay, so to talk about this one, we have to, I think it is better to know why we are going to talk about this property. So, I mean, in my point of view, I will ask this question, like, why do we need real line, like real numbers, instead of just stick with the rational number here? The reason is that there are a lot of holes in the rational numbers, even we have infinite rational numbers. Okay. For example, you can draw a line with square root of 2 in a real line, but you cannot find elements in the rational numbers that will equal square root of 2. So this kind of deficiency motivates the constructions of real numbers, and that real numbers is going to fill all the gap here. So how to draw a line of square root of 2 in a real line? We all know that in a right triangle here, if you have two sides that is 1 and 1, and then we know this will be, let's say this is x. So we all know that the very famous formula here, right? Right. So you already know, like if you have the knowledge of real line, you already know that this x equals to square root of 2. Right, so how to draw it in a real line? It looks like this one. So this is this thing is square root of 2. Okay. What else do I want to cover here? Yeah, so if you try to find, if you think of these questions, whether we can find a x in rational number that's such that equals to 2, you'll find it is impossible. And actually, we can construct rational numbers that, let's say that starting from 1. Okay, so this is Q1 and Q2 and Q3, that they are all in rational number, and it keep approaching this square root of 2. However, there's no way you can find elements in rational number that equals satisfy these equations. So that means in the words of rational numbers, there's hole over there, and that's why we need real numbers to fill those holes here. Okay, so formally we define the less upper bound property as following. So an order set X is said to have the least upper bound property if any non-empty subset E of subset E of X bounded above has the least upper bound L, which is in X. Okay, so this is, I think the last part is quite important. Okay, so let's go back to the way we construct the sequence here that approach square root of 2. Okay. Okay, so the way we